All right, we can get started. Welcome to Friday Night AI. We are very pleased to virtually have you join us tonight. My name is Rada Mihalcea. I'm a professor of computer science at the University of Michigan. I'm also the director of the Artificial Intelligence Lab. And about 2 years ago, we started the Friday Night AI series in an attempt to engage more closely with the community on topic of interest to all of us. I'm very pleased to have you all join tonight for a discussion on the role that AI plays in advanced air mobility. Next generation aviation will rely on AI to support autonomous and remotely supervised flight. Deep neural networks, which are computational architectures that are used for advanced learning and prediction models, will improve our ability to dynamically map and safely navigate complex terrain and urban landscapes. Mission and contingency planning systems can offer unprecedented support for in-flight emergency management to assure safety for the aircraft and people on the ground below. Because we need aviation to be ultra reliable and safe, safety critical AI must be assured and trust must be carefully calibrated. Tonight's discussion is about the aviation's greatest AI challenges and the rapid progress toward an exciting new vision of advanced air mobility for everyone. I'm joined today by one of the world experts in this space, Professor Ella Atkins. Dr. Atkins is a professor in the University of Michigan Aerospace Engineering Department, where she directs the Autonomous Aerospace Systems Lab, and is also associate director of the Robotics Institute. Dr. Atkins holds bachelor and master's degrees in Aeronautics and Astronautics from MIT, and master's and Ph.D. degrees in computer science and engineering from the University of Michigan. She is a fellow of the American Institute of Aeronautics and Astronautics, which is the highest distinction awarded to researchers making contributions in this field. Additionally, she served on the National Academy Aeronautics and Space Engineering Board and the Institute for Defense Analysis, Defense Science Studies Group. She has served on several National Academy study committees, co-authored study reports, including Advancing Aerial Mobility National Blueprint, which was recently last year, and also Autonomy Research for Civil Aviation Toward a New Era of Flight. Dr. Atkins had built a research program in decision-making and control to assure safe contingency management in manned and unmanned aerospace applications. And Professor Atkins also does field work. She is a private pilot and Part 107 UAS pilot. So before we get started, just a few logistics. For the first half of this Friday Night AI, Professor Atkins will address various aspects of the use of AI for air mobility. Then for the second half, you'll have the opportunity to ask questions. You can do that. If you are logged in the webinar, you can do that using the Q&A button at the bottom of the Zoom screen. If you are on YouTube, you can ask that in the comments. On the webinar, you cannot type questions in the chat, so please make sure you look for the Q&A button. With that, let's get started. And just an acknowledgement, tonight, Friday Night AI is a collaboration between Michigan AI, Aerospace Engineering Department, jointly with the Ann Arbor Public Library, which is broadcasting the event live on YouTube as we speak. So, Professor Atkins, I would love to hear more about you, and for the audience to get to know you better, can you share more about your career path, how you got interested in AI and what excites you about the field?
Sure. So when I was an undergrad and master's student in aeronautics and astronautics, I actually worked with space robots. That was a time where we were beginning to think about things like satellite servicing, where you would have a launched robot go up and try to do something to refuel or fix or deorbit another spacecraft. And so my master's thesis was in autonomous docking. But I recognized when I was doing that the the biggest challenges were really in how do you make sense of the data that is coming in and make decisions in what to do, even if you had noisy data and things weren't going quite like you thought they should. So then when I went back for my PhD after working in industry for a couple of years, I had to choose. I wanted to do robotics, but should I do aerospace or mechanical, or should I do computer science? And Michigan's AI lab was a perfect mix because there were people working with robots, but then I also had the opportunity to get a lot more in-depth knowledge about computer science and the state of the art in what AI means, and I guess maybe we're still deciding that, but then really learning some of the algorithms and techniques. And I never looked back, because to me, the most exciting kind of eye-opening thing I learned in AI was that you're not just limited to physics, that the model is as expressive as the human voice and all of the senses. And so there's really, we're just beginning to understand what that knowledge is and how you would apply it to things like advanced air mobility.
I like that. Indeed, there is so much expressivity on the AI side as much as there is on the what we are trying to model side. And you are doing research in AI for advanced air mobility. Can you share more about what this really means? You mentioned drones. Are there other autonomous air vehicles? Maybe also non-autonomous air vehicles?
Yeah, so if you go back, I would say about 40 years, you find the first fly-by-wire aviation systems. I know 40 is a long time ago. It's about 1981, I guess. That was the time where we took the mechanical controls out of the big airplanes, the tin cans with wings, so to speak, that we fly on when we go from place to place, and we replaced them with computers and wired networks. Why did we do that? Why did we go to these fly-by-wire systems? We went to them because they were lighter weight. They had more redundancy because it was not as expensive or heavy in weight to replicate wires and computers several times as it was to take all of the mechanical linkages and replicate those. Why do we have triple redundancy? Well, we don't want to crash. If something fails and you're in a car, you can pull off to the side of the road. If something fails and you're in the sky, it's bad news. So that's one of the reasons we're so safe, is that we have 3 of everything safety critical. Well, we still fly these systems. You and I, when we go to the airport, fly in flight management system equipped aircraft, but those systems were designed to interact with 2 human pilots. That means that a lot of the activities like checklists and procedures, all of that is managed by the pilot. And then when something goes wrong, the automation tends to shut down and the pilot has to do more decision making than normally. That led to having really good fuel management, software to manage things like staying on course as you go from point to point. So when we had the small UAS, unmanned aircraft systems, or drones, that came out kind of in the 1990s, was the first time that we had small enough computers with energy dense enough batteries to fly small things that became quadcopters that everyone could buy. But they started out fixed wing, and there's all kinds of configurations. We'll talk about that later if you're interested. But then we were able to do the same things on those small vehicles that we could do on the big jets. And so then we achieved kind of a state of the art where these vehicles can fly from point to point, but they need humans to supervise them because the humans enter the flight plans. Where are the points? What destination are you going to? And the specifics of the mission. So then we've become better at doing all of these things with a computer. And so the decision making now is more contingency management, which means what do you do when something goes wrong? Well, one of the challenges with any sort of system is if you throw control back to the human operator, whether it's a car, plane, or something else, and they're not ready to respond, you end up getting into trouble. Well, so advanced air mobility is the next generation of aviation. It's the generation of aviation where the software using AI will be prepared to respond to all of those things that pilots must respond to now. Perception. What if you see bad weather, you see obstacles on the runway or on the rooftop that you're landing on or in the field? What if you have a systems failure? What if there's other air traffic that's nearby? All of those questions right now are answered by human pilots, but we're beginning to get the software, the sensors and the software and the decision systems that can let us do this autonomously. There's not really a distinction in the long term between the type of aircraft and the size. What matters is that the decisions are safe and they're complete, meaning that the software doesn't suddenly shut down and say, I don't know what to do. And that introduces a whole host of challenges because right now there are situations where the software doesn't know what to do and when. So advanced air mobility started out as urban air mobility. And then people recognized that this was not all about urban flight, it's everywhere. So then the notion of advanced became inclusive. No matter where you're flying, if you have a vehicle that has the sensors, the software, the functionality to be increasingly autonomous, where in the long term it'll be fully autonomous, but in the short term, somewhere in the system there will be a human, whether it's a manned or unmanned aircraft. That's kind of what we're calling advanced. Advanced is a moving target like AI though, right? Advanced today may look different than advanced tomorrow. It'll be exciting to see what happens.
It's relative. And I want to just briefly pick on a word that you mentioned, increasingly autonomous. So I imagine there is a whole spectrum from fully human to possibly fully autonomous. The in-between, I think that's very interesting in terms of what it means to have that human AI or human system collaboration. What is the current sort of state of affairs in terms of that collaboration between humans and these autonomous systems?
Sure. The flight management system was the first step. The humans were able to do more managing and supervising of the autopilot systems, which allowed them to pay more attention to the higher level aspects of the flight, talking to air traffic control, managing weather-based decisions, and so on. One of the classic challenges with flight management systems is called automation surprise. Automation surprise happens when the flight crew, the pilot and the co-pilot, think the automation is going to do one thing and it does something different. And that happens because often the crew they're trained, but no one teaches the pilots the algorithms. They teach the pilots how to use the gadgets that they have. And nobody really, so for example, they don't teach them about the state machines or the control theory, right? That's not part of being a pilot. So there really is a gap between what the pilot knows and what the machine does. We've been trying to reconcile that with simulator time that allows the pilots to experience a lot of emergency situations that they don't commonly see when they have passengers on board. But there still is this automation surprise that has been responsible for several accidents, and we're gradually learning how to deal with it. There's going to be a whole new level of automation surprise in the future, and we should take away the surprise if we can. So the way we do that is by making sure that the interfaces between the humans and the machines are better, and to make sure that the machines don't just shut down and say, do something to save us, but instead they actually make a decision that is safe, communicate it, and then do it, which puts the human in a better situation than being told, save us. There are two aspects in aviation of increasingly autonomous systems that are really challenging to overcome. The first one is voice-based communication. If you've ever listened to a pilot in the cockpit of an aircraft, they talk all the time, not just to each other, but on the radio. They're talking to air traffic control and potentially other aircraft. Well, if we insist that increasingly autonomous aircraft, maybe unmanned aircraft to start with, process that speech, we're adding a burden to the autonomous vehicle that doesn't have to be there. Instead, there could be data link. We have data link now, but it's not used for safety critical instructions. That means that someone flying a plane is speaking about what their intentions are, what their flight plans are, not the computer sending a packet of data. So that's kind of a debate right now because the whole aviation industry expects spoken words to be the way of communicating safety critical instructions, whereas computers would be much better off with data link because it's faster, there's less delay, and it's more certain with respect to the content of the messages. The other thing really is coordinating traffic. Unmanned aircraft don't have eyes, so they don't see other aircraft. They're also very small. So human pilots using the Mark I eyeball, as they say in the aviation industry, are not able to see tiny quadcopters. That means that there's more risk of planes hitting each other because neither of them understands where the other one is. We have some equipment. There's this system called ADS-B, which is an industry standard piece of equipment to say where you are and that gets broadcast to other traffic. But it turns out they weren't expecting the kind of density that we will have with advanced air mobility of traffic. So it will become overloaded. So those are the two main problems: planes hitting each other and using voice-based communication and evolving to data link.
And for that, is there, I mean, I understand the speech part, for instance. Also for my own research, I know it's very difficult to understand human language. And you mentioned data link. And I would imagine that even for aircraft to communicate with one another, they could also communicate through data if there will be that kind of channel that they could communicate among themselves.
Yeah, they will have data link, but right now they don't anticipate requiring that air traffic controllers, for example, give instructions with a keyboard. They instead anticipate that for the next decade or two, maybe more, they will give safety critical instructions with their voice. Those decisions have to be shared with both the piloted, human piloted aircraft and the autonomous aircraft, which means that if we don't change the way air traffic control works, it's really forcing the autonomous aircraft to process that crackly radio signal when it's coming in and turn it into 100% correct instructions.
Well, and this, and also you mentioned pilots not understanding necessarily how machines work, which is understandable. And I guess we can say the same about us sitting on the computer science AI side, not necessarily understanding how pilots do their work. And so there is this gap, and I understand that you sort of try to fill that gap. You are both a pilot and also doing the research, so you have that understanding. But for how can we scale that up? Would that be like a requirement for everybody to be both pilot and do AI? Probably that's not tractable. So how could we?
I recommend it because the flying is fun and the AI is fun. Now, maybe you don't have a lot of free time after you do both of those things. I think one of the fascinating kind of push and pull kind of things right now is when you're making these widgets, these autonomy functions for aircraft. On one hand, making an expert system is a good thing because you're capturing the wisdom of 100 years of piloted flight. You can get checklists, you can get procedures for just about everything, the same kind of instructions that the pilots follow. And if you look at 99.99 with several 9% of the cases, the pilots are actually not learning as they fly. They are following procedures because that minimizes risk and it allows the experienced pilot to do something that they've done before, which is much safer. At the other end of the spectrum, you throw away all of that, right? No checklist, nothing. We're just going to do machine learning from data. And there's something to be said for that, especially academically. How much can you learn? What can you do? Are you going to have emergent behaviors? That's really cool also. I think there's a sweet spot in the middle where you can get as much as possible from all of this heritage of documented procedures that pilots use, but you also add in the machine learning because those procedures don't capture everything. And the more data that we have access to, as we've learned in other domains like self-driving cars, the more insights we can get by doing machine learning on it. So I think there's a lot of fun problems there.
And it's very interesting to hear you speak about that. I haven't really, I'm learning as you speak now about this particular space of AI and advanced mobility. But I've been hearing the same problems in other fields, like in healthcare, right? So we don't want to only have machine learning. We also want to have the domain expertise, like the doctors and nurses, and the same is in other spaces too. So reaching that sweet spot can be a challenge, but the fun challenges, as you said. And I'd be curious to hear from you also in terms of, as we make progress on this, what are some of the fields that will benefit from the advances that are done in this research? We hear every now and then these stories with Amazon who will start dropping packages on our porch with drones. And then, of course, we also hear about application agriculture when you want to survey these very large spaces and fields. And of course, there is more. It's also like just really autonomous flying. Can you tell us more about what are the areas that will eventually see the first benefits from this kind of research?
Sure. I think one of the most compelling applications for the small unmanned aircraft right now is the humanitarian mission. There are several companies, I'm not going to name any right now, I guess, but there are several companies trying to open businesses to deliver medications, to pick up blood samples and so on. They are being welcomed in countries that don't have really good connectivity with roads between places. And also in these areas of, I guess, primarily right now, Africa and some parts of Asia, you find that there are almost no aircraft, which allows you to fly over rural areas where you're not going to hurt anyone if you crash accidentally. But also there are not a lot of rules or not a lot of risks of hitting other aircraft. So it's allowing these small UAS to really get started today, going pretty far to deliver medications, for example. So right now I'm on a couple of committees that are trying to figure out the rules. How do you define the risks on the ground as well as in the air, and use those to set rules for these small autonomous vehicles? Other applications right now, airborne inspection is huge. So in Ann Arbor, we have a company called SkySpecs started by some University of Michigan students who are now well beyond studentdom to run their own company that is doing wind turbine inspection. So every so often, you have to inspect at very close distance the blades of the wind turbine because they get damaged by things ranging from small debris, rocks, and so on to lightning strikes. And obviously it would be a bad deal if they were spinning fast and a blade fractured and flew off. So that company has been doing very well at they still fly with human supervision, but getting to the point where the inspection process itself is autonomous, where they follow the blades and collect the data. There are railroad track, power line inspections, for example, in California, where they've had really big problems with power lines resulting in wildfires. The drones are helping them get out to see their power lines more often, which in the long term will help them reduce the probability that there's going to be a wildfire caused by one of their electric lines. all of these missions that I mentioned about the sky specs inspections of wind turbine blades, the power line inspection, we're also reducing risk to humans, because before, with the wind turbines, someone had to actually rappel down the blade to inspect it, physically going down from the center of the wind turbine to the end of the blade to look at it. Now everyone gets to stay on the ground. With the power lines, a helicopter would need to fly at very low altitude, or else someone would need to climb up from the ground or with a bucket truck to look at the power line. Now the drone can actually fly pretty low to the power line and not involve any sort of human who might be at risk near the power line. Many other applications: bridge inspection, construction site inspection, a lot of videographer work. This image that you see right here of the robotics building was taken by one of the University of Michigan videographers. But if you look at this picture, it was taken from the air. So he was flying a drone to get this picture.
Very cool, very cool. And I could see also other applications, just exploring spaces that cannot be explored otherwise.
Oh yeah, and doing, just like with the robots that crawl and walk and so on, any sort of hazardous site. I know some people that are doing mine inspections, underground sewer inspections, and so on. So yeah, lots of applications.
And I would ask one more question before we move to questions from the audience. Whenever there are AI tools that are being deployed, there can also be ethical concerns. So can you share more about what are some ethical concerns associated with development or deployment of such AI systems for advanced air mobility?
Sure. Let's go with two tracks here. For the manned aircraft track, that means that there'll be, for example, passengers, like an Uber ride where instead you're in the air instead of in a car. I think the ethical question there is the same as the ethical question for self-driving cars. How long do you wait to prove the system before you allow the people to get on board and go? We're never going to get at 100% of reliability. But again, that trust calibration thing, when do we have enough trust in this autonomous system with no human pilot backup to let it go? And let's say that we do have thousands and thousands of these little air taxis running around with passengers in them. The pilots are not going to have as much training as the airline pilots have. There are just too many vehicles that are going to be up in the air at once. So they're going to really be more like the Uber drivers when you get in your car at the airport to go somewhere. These drivers are fine, but they could be like 18 years old, having driven only for a little while. So you really need that automation to be up to par so that you're safe, despite the fact that you have a pilot with much less training. And that pilot needs to understand when to fly and when not to fly, when to trust what the system is doing versus saying, well, something's not right, and telling the passengers, I'm sorry, I can't fly right now. In the small realm, the small UAS, most of the ethical questions, once you get past the notion that one of the drones might fall from the sky or that you might hit another aircraft with it, come from the use of onboard sensors. You can take an awfully lot of video that we couldn't take from the ground. We have privacy fences and all kinds of things to block our, windows of our home from plain view from people who might be walking or driving by. Now, all of a sudden, none of that matters because the drone can hang out outside your second floor window anytime it feels like it. Does it have permission to do that? Who would give it permission? There are a lot of discussions right now about how we make sure that we still maintain our privacy and access to our own backyards and airspace right around our house, even though we want to welcome these things later, and hopefully they won't be too annoying.
Yeah, this really raises a lot of interesting questions, because we are in a world that traditionally has privacy protection on the ground, not in the air, right? We didn't really assume that there will be things flying around. And so that it's really just setting a whole set of new rules and thinking afresh what privacy in the air really means.
Right, because companies will say, trust us, we're not going to share our video. And you're like, well, once the video is there, it never really goes away. Somebody stores it somewhere in a vault of bits and bytes that might be pulled up in 10 years and show up in court.
Yeah, and that's there, but this, like you said, it raises interesting challenges. We'll have to figure out so we benefit from the technology.
Yeah, I think there's also one more thing to say about this. I think if you think of defense and aggression type of applications, the more autonomous capabilities, the more AI we put on things, there's a lot of people are afraid that we could end up having wars start because of the AI. And that's kind of goes beyond just the air vehicles. It would include anything that was weapon-like. I think the plan would be that there's always a human somewhere in the loop making decisions about whether to release weapons, but there are some movies and some scary videos that have been put out that say, well, the AI is going to cause bad things. And I guess I want to advocate for separation between the flying vehicles and the weapons. The flying vehicles themselves, they might have bugs in their code. They might not be able to use perception perfectly, so they don't notice an object on the runway. But the weapons don't have to be put on them.
Yeah, and that's also part of the reason why we have this series of Friday Night AI for people like you to share what sort of the real side of AI, because there is indeed a lot of media out there that portrays, I would say, the wrong side of what AI could do. I mean, there are so many limitations to what can be done. And
yeah, I mean,
AI is really hard.
We're doing things like, see this rooftop behind us in the robotics building. We're trying to automatically map whether there's a potential landing site that would be safer than landing on the street, for example, for a little drone. In densely populated cities, that's one of the things you might want to do. And people who fly fixed wing aircraft are looking right now at, can you be trustworthy in figuring out if there's any sort of obstacle on the runway? So these are kind of, they sound like boring problems, but they're really important to keep you safe, because hitting a deer on the runway with a fast moving plane is much worse than even hitting a deer with your car on the road.
Yeah, I could imagine that. So we are now at the time of getting questions from the audience. So please, if you are watching from YouTube, just type them there in the comments and they will be passed to us. If you are watching from the webinar, you can just put them in the Q&A. And while you are doing that, Professor Atkins can share a little bit more, since they say a picture is 1,000 words and a video is 1,000 pictures. We can see a couple of videos to learn more about her work.
Thank you. This is me shamelessly advertising some fun stuff, but it's all so much fun to fly these things. So this is my lab in the new robotics building from the aerial perspective. So we have a 3-story flying lab. Oh, they're flying into they weren't actually supposed to do that. They're flying around the actual lab area. So you can see some quad rotors. You'll see those outside in M-Air, which is the 50-foot netted facility, pretty soon. So we're actually right next to the walking robot lab, so we can see each other. They watch us fly and we watch them walk. One of the things that's cool about the drones, though, is that vertical motion is just as easy for them as horizontal. So they can really get up to hard to access spaces fast, as you can see from this. We all watch each other here, so we can also spy on students in labs. All right, let me stop this one.
This
So
really illustrated what you were saying earlier, that people who designed this building didn't think that you would need some protection for those windows up there, because who would go there and watch?
right. Yeah. I mean, we watch the robots. That's all we see. And we get to see the students working on their lab projects. But if those were house windows, then no problem. The drone can zip there in just a few seconds. So the other one is we have this netted flight facility called M-Air. And my students have been taking advantage of that. It's a lot of things that are maybe a little more risky you want to do inside a net. So right now we have one drone with a camera on it taking a video of another drone doing something for research. So in this case, where we have a drone that's just flying an inclined circle, which allows it to go up and down 3D motion around a pretty tight turn. We're testing different flight controllers here. So it's not tremendously exciting, but for the student, it was exciting because we got some new data on some of the software for flight control that allowed us to benchmark different forms of control laws. And then this will transition to autonomous roofing. So one of the things we tried in the realm of physical interaction tasks is actually nailing shingles on a roof at different slopes. So this is completely autonomous. The robot is flying down, you can see in the upper left corner of the video, to the roof surface and using kind of a haptic feedback type system to apply the right force. This is cooperative payload transport, where these 4 drones are working together to lift this payload and carry it around. We're about to release a new video and paper where the drones are being guided by someone pushing on the payload as haptic feedback. This would allow a completely heads-up interface. If you're in, for example, a disaster zone where people don't have any experience flying drones, instead of them using a tablet or an RC controller, they would push on the payload to get it where they wanted it to go. This is a quad plane, which is the simplest possible combination of a fixed wing airplane that's really cheap and a quad rotor. So here we're doing some tests of transition between forward flight and vertical flight. This airplane is being flown at a model aircraft field between Ann Arbor and Ypsilanti. We, of course, have to ask the university for permission because we have a safety committee that would authorize this. And we purposely fly at a model aircraft field because those fields are set up to separate the people from where the aircraft flies. So this allows us to have an extra layer of safety. We know that we're never going to be flying over people. And as much as we'd like to think that our stuff is perfectly safe, the students are doing first run research level software, which means that there are some bugs. I know that may surprise you, but in flying, when you have a bug in your software, often what happens is the drone will crash in like a second. And then you just look at it going, I wonder what happened. But we don't show crashes here that much. If you want to, I actually have a crash compilation, but I think maybe we should go to questions now.
And that's interesting, is the side of AI that comes with costs. Like, what is the cost of a bug? It's a new drone. So you start again with that bug fixed. Well, thank you. This is super interesting. And I think it also speaks to what you were mentioning earlier, all these applications that can complement or help us as humans in what we do. So instead of climbing on the roof to change the shingles, if we could have something do it for us, I could see a lot of benefits in terms of safety. So we have a few questions that came in. One question is asking whether this work is also applicable to the task of automating large air vehicles like passengers or cargo planes, as most of the conversation that we had so far was around smaller vehicles.
There is a surprisingly large amount of software that is exactly the same on the big aircraft and the small aircraft. The control problem, if you have a fixed wing aircraft, it doesn't matter how big it is, very similar. The navigation problem, whether you use GPS or other radio-based navigation aids, also very similar. The main difference, well, the main two differences are whether there's a human pilot sitting up front in the vehicle versus a human supervisor on the ground. And the second one is just where you fly. Right now, we ask the small unmanned aircraft to fly at low altitude to keep them separate from all of the manned aircraft that are flying above 400 feet above ground. So they're not sharing the same airspace. And that involves all the things I talked about earlier with voice-based control and them being able to see each other and so on. But the technology is very similar. You need a lot of the same software.
I would imagine also for passenger aircrafts to also have a different level of security, similar to how pilots need a much larger number of hours of training to go on a passenger aircraft.
Yeah, there's also some other factors. People are already a little bit afraid of flying, especially people who don't fly a lot. We're pretty confident that passenger carrying aircraft are going to be one of the last types of air transportation to become fully autonomous, because people like to have a human pilot up there, up front, to make sure things are safe. And that's just kind of an emotional thing, regardless of whether the autonomy was certified. And the other thing is the larger aircraft have a lot more risk, not only to the people on board, but the amount of damage they would do when they hit the ground.
Right. There is another question on the communication between unmanned systems and pilots. What approaches do you think are most promising for these systems to be able to understand instructions made for pilots? And of course, you mentioned speech, which is sort of the current way of pilots communicating between themselves. And then the data link. Is there also something in between? Like, what are some of these approaches that could work best?
So the actual transmission of data is either going to be voice or data link. Those are really our two options. But when it's data link, there are a lot of questions in how does that information get presented to the pilot? What are the interfaces? What kinds of screens do they see? How do they switch between them? Which instructions or data sets are announced to the pilot versus on demand, meaning that the pilot can choose to see the data or ignore it. On voice, the pilot hears everything that is said. And sometimes that's very distracting and delay inducing, because the pilot hears everybody on the same frequency. So sometimes, I know this as a pilot, you'll have to just wait your turn to say what you need to say. If it's a very crowded radio channel, then you may have to wait for a while. That means that you can't ask for information or request a clearance. You just have to wait your turn. So it's about time. Let me also give an example of how data link would have made a difference. So you guys probably have heard of the U.S. Airways flight in New York that ended up in the Hudson River, where Sully was the pilot. There was a movie made about it, hit geese, lost its engines, and it had to land. If you listen to the cockpit voice recorder, which is the human voice, or the air traffic controller recording that was made, what you find is that Sully should have screamed. Nobody says that, right? But I say that. And it's pretty clear. Nobody disagrees with me when I say this, because he was so calm when he talked to the air traffic controller. The air traffic controller did not realize that he had an emergency. It took him about 15 seconds to say, did you say that you lost your engines, that you had 2 bird strikes? There was this little dialogue going on. That was about the amount of time they had to turn back to the runway and land safely. So after that 15 seconds of the air traffic controller not recognizing that Sully needed to come back to LaGuardia, he couldn't anymore because the plane was losing altitude the whole time. And he couldn't just turn back without the air traffic controller knowing, because there were planes coming out of LaGuardia Airport the whole time. So that is a case study in, yes, everyone lived and Sully was an awesome pilot, but that's a case study in how voice can be problematic.
And it's interesting also, since you mentioned data link, so screaming is in human voice, right? So we have this way of expressing urgency, but when it comes to data, it will be probably some codes in there that would indicate emergency. So for the data to scream, to pay attention. And I see there is a follow-up on the question that it's also about written flight instructions, not necessarily real-time communication. I don't know if you wanted to add anything. You did say that the data link has an entire spectrum. So talking about written flight instruction, what are the most promising approaches there?
Written flight instructions. So like checklists, is that, maybe that's what's being mentioned?
Yeah, I think it's hard to do a back and forth with the question asker. I would imagine it's about the data link itself as a written form of instruction.
Yeah, so I guess to me the term written can be very general. So if you have a tablet or another kind of LED, LCD screen in front of you, you can put on it whatever you want to. And one of the things also that happens in aircraft is you don't just use vision. You use audio, you use sensing for haptic feedback. You're trying to get as much information into the human as you possibly can. So with the data link, there may be interfaces that involve not only written or graphical information on a screen, but also reproduction of voice. There's no reason that the data link can't end up sounding like a computerized, I don't know, weather forecast on the Weather Channel, you know, where it says, today will be cloudy. And you know it's a computer, but you can still understand it, even if it's kind of boring. So I think we're going to have that with the data link, especially and as long as the pilots like to hear that type of auditory information.
Okay, thank you. And we also got a confirmation that that's what they were asking about. So.
Yeah, the checklists, that's easy to program. One of the reasons flight management systems did not do that automatically is that you have to have the pilots be engaged. One of the things that helps the pilots stay in the game, stay focused on what's happening with the aircraft, is for them to lead the checklists.
We have a question coming now from someone who is interested in the space that you are working in. So the question is, how would someone who's interested but unexperienced start in this area? Are there certain maybe courses online or at Michigan, or books or papers or opportunities? What would be a good start?
Yeah, I don't know who you are. I don't know what age you are, but you should come to the University of Michigan as a student if you are K through 12 or an undergrad seeking grad school. I made the switch from aerospace to computer science between my master's degree and my PhD. I had to catch up a little bit, but it was fun. Maybe I spent, I would say, an extra year getting my PhD, because I spent the first year completely immersed in coursework that I hadn't had. But it really was nice to have both fields. If you're a practitioner,
they are sophomore, considering a sophomore at UMich, considering grad school. But I guess even general pointers, maybe there are other people in the audience.
So grad school is, it's, you know, if you're in a STEM field, you can change. I know in robotics we have a very diverse population of students that have undergrad degrees ranging from physics to computer science and aerospace and mechanical, all the different engineering programs. And I think that's, if you have the energy and interest to do it, that it's possible. If you are older, then there are some online courses, but I guess I would say most of those are, you have to do the homework if you want to get into it, as opposed to just listening.
Yeah, and I think it's really like, I know you were asked, not me, but in general, like if you really want something, you can just go out.
Yeah.
It's really, to me, what the part that is really required is interest and will, and then everything else follows. So.
Well, and for flying, go down to the Ann Arbor airport if you're in Ann Arbor and just look around. There's I don't want to advertise one place versus another, but there's at least 3 different places that train people to fly. It's pretty easy to find them online. And most of them have things like discovery flights where you can go up for half an hour with a flight instructor and see if you like it.
Yeah, and that's, I think, for people in Ann Arbor, I think that I've been there once. It seems like a great place to start exploring. There is another question saying that the question asker, they grew up listening from their dads talking about 747 Airbuses and so forth. And the question is asking whether some of the commercial airplane models today use any drone or AI components.
Well, I guess I would say drone components are shared with all other aircraft. So if you think of a little microprocessor board that might do something on a commercial jet, so simple as moving the rudder, right? There's a computer right there next to the rudder, which is the vertical fin that sweeps back and forth, left and right. That's networked to the rest of the aircraft. So if you look at the processor that's right there controlling that rudder, that is not even as sophisticated as most of the processors you find on a quadrotor. It's just that that's not the only computer on a modern jet airplane. It has many computers networked throughout the vehicle. So there are, batteries, motors, computers, all of those components are in many of these devices. I guess, again, it seems like they should be vastly different, these little vehicles that you can hold in your hand and launch into the sky versus the giant vehicle. But it's really a matter of complexity and size. There's just so many pieces and parts that go into the big airplanes that they seem like they're really complicated, and they are because the manufacturing takes so long. But the basic functionality is surprisingly similar. And so we're really fortunate that we can get out and fly quadrotors and little model aircraft today and have a lot of the same data capability and software testing, including the AI. Perception is perception. One of the things that the big airplanes have to do for the next level is detect and avoid. They have to detect other airplanes and avoid them. They have to detect objects on runways or wherever they're landing. If they're a helicopter, a big area that's suitable for landing, they have to make sure there's no people or other debris there. So it doesn't matter whether you're a quadrotor, survival flight, helicopter, or fixed wing airplanes. Your perception problem is to look around, make sure it's clear, not hit anything. Your decision problem is, how do I get to my destination safely? And your actions are, how do I move the control surfaces or motors to go the right place and talk on the radio or data link?
It's interesting because we think of like small things would require small AI or technology, and big things would require big technology, but sometimes that may not be the case. And a related question is about what you mentioned earlier, that there are opportunities to combine some of the traditional documentation and procedures with modern machine learning. What kind of data is needed to help make that happen?
If you have data, please send me email. Big data sets, even though aviation has been collecting data for a long time, the data sets are not available to academics to use and publish freely because the data has monetary value, it turns out. The biggest data sets in aviation, well, we have just now begun to collect accident data for cars in an organized way. The NTSB, National Transportation Safety Board, has been writing detailed reports on aviation accidents for 60 plus years. We have so much data. Right now, if I want to get the black box data, the black box records what's going on the airplane. And if in case there is a crash, you can play it back. We have that data as spreadsheets for almost all of the accidents that involve US airplanes or US carriers on the NTSB's website today. So we can download that data, play it back, and use it for our research. But that's not the high bandwidth data. So what do we need? Well, we're increasingly equipping airplanes with cameras so they can see what's in front of them when they come in to land. Now, if they're landing in the clouds, that doesn't matter. They can't see anything. But if they're doing visual approaches to landing, whether it's a helicopter or fixed wing aircraft, that data has the same machine learning problems as the self-driving cars do. Can you see where you're going and make sure that you're lined up with where you need to go and make sure it's clear? Other data sets, we have been increasingly putting cameras in cabins of aircraft. Having unruly passengers is more of a thing now than before COVID. If you've been looking at the news, there just about every other day you see somebody that's been in a fight, attacked a flight attendant, gotten thrown off of a plane for not wearing a mask, whatever. And so we've really begun to do things like collect video so that we can see what is going on with the passengers. And pilots don't want this, but we're increasingly thinking of eye tracking systems and cameras looking at the crew so that the system can tell what's going on with them in case they become incapacitated or confused. Probably the biggest money maker of data is maintenance. Both Boeing and Airbus, the two biggest jet manufacturers, have tremendous monetary value in collecting all of the networked data on engines, electronics, every system on the aircraft. For those of you that have been flying for a long time, maybe you've noticed that the number of times that you have to not fly due to maintenance is drastically lower now than it was 20 years ago. That is because of the big data that has been collected by both of the aircraft manufacturers and used to predict with prognostics what parts are needed and when, and to get those parts to where they need to be before the plane lands.
And that's not a small contribution, I guess.
No, it's huge, right?
It's times, and yes,
it saves. The airlines are happy to pay the companies because they suddenly don't have 100 angry passengers at the gate wondering when the plane's going to leave.
And you mentioned possible situations when, say, the pilot becomes incapacitated for whatever reason, or there are other such situations. And it could also be, and this is another question that was asked, that the command from the human pilot would contradict with, say, environmental conditions. Could that be detected by the system, that there is this contradiction, and maybe help resolve it somehow?
Yeah, so right now on the big jets, we have what are called envelope protection systems, which keep the pilot from stalling the aircraft, meaning pulling up too steeply in the wing, losing lift. We have runway overrun protection systems, which makes the plane either automatically take off or put on the brakes and stop so that it doesn't run off the end of the runway. And we're gradually getting more. These systems are a little more like adaptive cruise control that doesn't hit the car in front of you, or lane keeping where you don't cross the lines when there's someone in the other lane, in that they're kind of just guiding the pilot not to make mistakes. In terms of the things like flying into bad weather, let's say there's a thunderstorm and it looks bad. Right now, the aircraft do not stop the pilot from flying into anything that looks bad. Or even flying into another aircraft. The collision avoidance systems right now are alerts, but the pilot has the option of ignoring the alert. One of the reasons historically that that's been the case is that you have false positives. Sometimes the alert goes off and there's not actually another aircraft there, or you have a situation where the pilot chooses an evasion maneuver that is different than the one that the system recommends. So right now, collision avoidance is completely manual up to the pilot, not done automatically. We have algorithms that are beginning to work pretty well, so I expect us to transition to them. One military case, which is really awesome, is something called terrain avoidance system. So it's GCAS, ground collision avoidance system is the acronym for it. A lot of fighter planes in particular tend to hug terrain, be below the radar, all of that. But it's really hard for the human to see in time to avoid obstacles all the time. So there have been a lot of planes lost, a lot of human lives lost because you're flying so low and you don't notice something. So that system protects you, whether the pilot becomes incapacitated or whether the pilot just doesn't notice something that it is going to hit. That automation now pulls up when needed or turns around it. In terms of incapacitation, most aircraft will still do what the pilot tells them, even if the pilot is incapacitated. There have been some classic cases of planes running out of fuel because the pilot was incapacitated and it just kept going in a straight line. That is connected to my eye tracking comment from before. If the human is slumped over in their seat, then the automation would know that it has to act without instruction.
Thank you. And I have here another question, which is something that I'm also wondering as well, in terms of environmental conditions, what we were talking about earlier. You mentioned Sully and birds. Have any drones interfere with birds? And is there any data on how birds react to drones in the sky?
Yeah, so there are some classic videos. There are a couple of videos where like an eagle or a hawk actually grabs the drones and like makes them crash. Those are fairly rare, but the little drones have been attacked by the larger birds before. In general, people have used birds or drones to try to track flocks of birds migrating, for example, or just flying around in a habitat. They don't always act the same, but my understanding, I'm not an expert in this, is that if you surprise the birds, then they don't behave normally. And if you kind of just hang out, they make a noise, but the birds get used to it and it doesn't matter.
Yeah, I find that very interesting, which also goes into interdisciplinary spaces, like how would people who study these birds and habitats, how can they make use of these advances in AI and advanced mobility to make advances in the study of that, of nature, really. Mm-hmm. So we'll take just one more question as we are past the hour. So there is the question again about communication, which seems to be a major part of how this works. So most people parse audio faster than text. So in terms of going back from the system to the pilots. So in terms of communicating, would the flight crew have an easier time communicating with speech rather than reading information? And so then the follow-up question to that would be whether there is potential for cross-disciplinary work with linguists here as to what would be the ideal communication.
Yeah, so I think one of the questions is as we have increasingly autonomous systems, what is the role of the human and what is the role of the machine? This is a classic question that we ask in many domains. And if the role of the human is to make mission level decisions as opposed to course correction type of decisions, then the amount of data that has to be presented to the human is not as fast. So those tend to be minute to hour timescale decisions as opposed to the second to second decisions that you would have if you're holding a joystick and trying to move it in the right way. I hear you literally, and totally agree that if the human is processing the auditory information more effectively, then that's how it should be presented. which is why I was going down the path of get the Weather Channel voice and present the information. I remember when I learned to fly, I was actually, this is kind of sad, I was more afraid of talking on the radio than flying the airplane, because I was afraid that I would get on the radio and not be clear enough, and the air traffic control would have no idea what I was saying, that I wouldn't be professional. So my flight instructor had this. She gave me a 3-page document that had instructions. Here's what you say, here's what they'll say. And so I used that for probably a month before I threw it to the side and said, okay, I know enough to talk on the radio. So there's already a language that's been developed, standard ways of announcing what your plans are, standard ways of air traffic control responding. In fact, if you don't answer with one of those standard commands, and it's not just a friendly kind of greeting type thing, air traffic control will become concerned about you. So linguists, I think, it would be great to have that collaboration as we begin to transition from pure voice to a mix of voice and data link. I think that, again, it's a matter of having the information of what has been done in legacy aviation, these scripts of what you're supposed to say and when, mixed with the new information that goes along with the changing roles of the humans and machine.
And in general, I think the future belongs to interdisciplinary collaborations. I mean, yourself do that, AI and aerospace, linguists and other experts will probably have a lot to say and contribute.
Yes, so and we should talk about that sometime. Maybe not on Zoom, but yes.
Definitely, definitely. So thank you very much for sharing all your wisdom here. And I feel I learned a lot. I know about AI. I don't know about AI as applied to aerospace. So this was very interesting. Many thanks also to the Ann Arbor District Library for hosting us, and to the audience for listening to us and for all the great questions. And we'll see you for the next Friday Night AI. Have a great weekend.